first function is the 3x squared plus x. The second one is x to the 1/2 is how you're going to write that when you do the derivative of that one. So if this is f and this is g, then your derivative of the first one, that's pretty easy. That's just 6x, right? Plus 1. And then the derivative of the second one, this one's a little bit different. So think of this guy as x to the 1/2. So that's going to be 1/2 x to the negative 1/2. I would actually recommend leaving it like that and then worrying about it later. Like leave it as a negative, because then when you're multiplying and stuff, you can just add your exponents that way. But you can, I mean, if you put it in the denominator, that's fine. It's just harder to manipulate. So then you're going to say the derivative of the first, well, that's just 6x plus 1. And I would write this guy times the original x to the 1/2. I would write him like that, okay? And then you're going to say plus that 3x squared plus x, and then times 1/2 x to the negative 1/2. And then we're going to just distribute. So just put it through and add your exponents, right? So we're going to say 6x to the first power times x to the 1/2 power is 3/2. So we're going to say 6x to the 3/2 plus just x to the 1/2. And then here we're going to say 3/2 because we're multiplying by this 1/2. And then we're going to add 2 and negative 1/2, which is also 3/2, right? So x to the 3/2. And then plus, we're going to have another 1/2 there, and this is just going to be x to the 1/2. And then you're just combining like terms, right? So we have 12/2 and 3/2. That gives us our 15/2, x to the 3/2. And then we have the 1 and the 1/2, so that is our 3/2, x to the 1/2. So the formal definition is f of x, if it is a composite function, u of f or u of v, which we know what composite means, like one function inside another, where u and v are both differentiable, then the derivative of the function is the derivative of u times, or the derivative of u with the composite times the derivative of v. So here's how I say the chain rule, right? The derivative of the outside times the derivative of the inside. That's how I say this rule. And so I'm going to show you why that verbiage makes sense, all right? So when I look at example 3a here, my outside function, like what I would call my outside function, would be this 2 times this guy to the 3rd power, right? So that inside piece I actually ignore when I'm doing the outside derivative. So he doesn't change at all for this first step. Derivative of the outside would mean I'm going to apply my exponent rule. I'm going to take the exponent of this guy and multiply it in front. So I have 2 times 3, that gives me 6. Leave the inside alone. And my new exponent of the outside is going to be what? 2, right? Easy enough. And then I am going to multiply that by the derivative of that inside piece. The derivative of the inside piece is the same thing, 2 multiplied in front, so that's 2x, and that minus 1 drops off because it turns to a 0. Derivative of a constant is 0, right? And so then I'm just simplifying. So I'm going to take the 2x and the 6, and I'm going to say 12x, x squared minus 1 squared. And you do not have to FOIL it. Leave him alone. All right, leave him alone just like that. In the book, they FOILed it. Don't FOIL it. All of this words up here just means derivative of the outside times the derivative of the inside. So let's look at the second one. What would my outside function be? Well, it's that whole group that is being taken the cubed root of, right? So anytime I have a root in derivatives, typically I'm going to rewrite it to a fractional exponent to make my life easier when I'm doing this. So the first step before I differentiate is to just rewrite him. So I'm going to say x squared plus 7x to the 1/3. And now you can clearly see what your outside function is some group to the 1/3. So I'm going to take the derivative of the outside. I'm going to multiply by the 1/3. 1/3 times x squared plus 7x, leave him alone. And then I subtract. What's 1/3 minus 1? Negative 2/3, right? And then I'm going to multiply by the derivative of this inside piece. The derivative of the inside piece is just going to be 2x plus 7, right? Multiply by the 2. I personally would just do numerator denominator here. I don't know how they did it, but that's how I would do. So in my numerator, I have the 2x plus 7 and the 1. So I just have 2x plus 7 up here. And in the denominator, I have the 3. And because that's a negative exponent, I have x squared plus 7x to the 2/3. You can leave it as to the 2/3. You could put it the cubed root squared. Usually you're going to see it actually with a fractional exponent down there, but sometimes they'll convert it back. Either way is acceptable answer. All right. So the derivative of sine is simply cosine. That's nice. So when we are looking at something like slope of the tangent, and the proof is actually in this. If you think about the sine graph, it just slides 90 degrees to get to the cosine graph, right? And so the slope of the tangent kind of just curves with it, and it just follows that slide is basically what happens. And they're about to, actually they do the derivative here with the derivative, the outside times the inside pretty much is what they do. So this is when you're memorize, and you're going to memorize A here as well. So the derivative of sine is cosine. The derivative of cosine is negative sine. They just show you why for the proof of it. And then cotangent, we're going to use the quotient rule to solve for. So the derivative of cosine, then we could rewrite the cosine of x. If you'll recall, way back in your brain, is that it looks something like this. Remember, you could do your even and odd functions and all those functions that we did. And so we said sine and cosine are 90 degrees away from each other. And so you can rewrite cosine as just 90 degrees minus the x, and you would have sine, right? And so we can just rewrite it. And so now we can do if we're trying to find the derivative of this, we can do the chain rule, okay? So the chain rule, anytime you have a trig function, typically your trig function is your outside function, okay? Typically. I say that because you can square a trig function and then all of a sudden that's the inside function. But so typically when you have sine or cosine of something with a group, then your outside function is going to be the trig function itself. They told us what the derivative of sine is. The derivative of the sine here is cosine. So if I'm taking the derivative of my outside function, then I'm going to say, well, that's going to be cosine of pi over 2 minus x, right? So far, so good. That's my outside. And then the inside derivative is this. Now, remember, pi over 2 is just a constant. It looks like a variable, but it's not. So that piece zeroes out. And the derivative of that negative x is just negative 1, right? Negative 1. So far, so good. All right. If I look at this, what is the cosine of pi over 2 minus x? That is going to be sine of x, right? So this is sine of x times negative 1. Another way to write that is negative sine of x. This is one you want to remember. So the derivative of sine is cosine. The derivative of cosine is negative sine. Okay? That's what you just need to remember that, because you're going to then use that like till you're no longer in calculus, pretty much. All right? So then let's look at cotangent. All right? Cotangent is one you're going to end up memorizing, but this one you can actually also see where it comes from. I can rewrite cotangent, and how can I rewrite cotangent? Cosine over sine, right? Yep, so cotangent is cosine of x over sine of x. And now, because I know what cosine is, and I know what sine is as far as derivative goes, I can do my quotient rule, right? And so if this is my f and this is my g, then the derivative of my f is going to be negative sine of x. The derivative of my g is going to be just cosine of x, right? And now I can do my quotient rule here. All right, so quotient rule says the derivative of the top, that's this guy right there, times the bottom just the way it is, minus the top, derivative of the bottom.
Where'd you get the negative from?
So when I'm doing my quotient rule, this is the prime there and the regular function there, prime there, okay? And then it's all over the bottom squared. Right? So far, so good? Okay. And then from this, I am going to just do some basic algebra and then some trig rules, okay? So negative sine times sine is negative sine squared of x, minus cosine is cosine squared of x, all over sine squared of x, right? What do you think I can do on the top? It looks close to something, but not quite. You don't have to do the conjugate here because they're already squared. So think about your Pythagorean identities. Yeah, it's going to be 1, but what do I need to take out of the top? It's a negative. Technically, sine squared, positive sine squared plus positive cosine squared is 1. So if I pull a negative out here, right, I'm going to scoot him over a little bit because we're running out of room. All right, if I pull a negative out on top, then I have sine squared of x plus cosine squared of x, right? That is a trig identity, Pythagorean identity. Sine squared plus cosine squared always equals 1. So that leaves me just a 1 on top. Negative 1 over sine squared of x. I can also rewrite 1 over sine squared. What is 1 over sine squared? Cosecant squared. So I have negative cosecant squared of x. The derivative of cotangent is negative cosecant squared. And that's something else that you're going to remember. But if you don't remember, you at least should know cosine over sine and your quotient rule, bare minimum, right? And so we will, in calculus, get to where we have the 6 trig functions memorized because it's just easier. It's much faster to just know the derivatives than to go through this process every single time. But this shows you where it comes from, all right? Natural exponent function, e to the x, all right? So this comes into play when you get into logarithms, which is pretty far into calculus. It's probably 3 or 4 chapters in. But they're just giving you the basics here. E is actually one of the easiest functions with derivatives because you can see what the derivative of the e function is, right? Technically, the derivative is e to the function times the derivative of the function. But right now, they're just introducing e to the x, and the derivative of x is just 1. So e to the x times the derivative of x is just e to the x. If that were e to the x squared, it would be e to the x squared times 2x, right? It's like almost like the chain rule there that happens. But I think here they're just going to leave it as e to the x. So the derivative of the natural function e to the x is just itself, all right? Now, I want to point out e to the x is a function, e to the second power or to the third power is a constant. It is not a function, okay? It's not a function of x. It is a constant, just like pi is a constant, okay? So you'll notice here in this example that they have e to the x, which is going to require a derivative, and then they have e to the fourth, which is just a coefficient, okay? So don't confuse them. Don't repeat it when it is a constant. So in this case, I'm literally just saying, okay, well, the derivative of 15 e to the x is just 15, the constant, times the derivative of e to the x. So this piece is just going to look like that. All right. And then here, this is a coefficient. All right. And so I have e to the fourth times the derivative of that guy. The derivative of that guy is negative sine of x. And so this whole derivative is going to look like this, 15 e to the x minus e to the fourth sine of x, right? So the natural function is really easy to derive, and it's just as easy when you throw something other than x up there. You just end up using the chain rule when that happens.